Hi ladies and gents, we are in Unit N, taking a look at calculating probabilities in the normal distribution. Now in the last one we took a look at just running through a whole bunch of different problems where we were given the mu, we were given the sigma, we were given the x, and we were asked to find the probability. What if one of those is not known and instead we're given the probability? So this paragraph here, I'm just going to read this. Sometimes a probability value, usually expressed as a percentage, is given in a problem, and the student is asked to calculate the corresponding x value or the values of one of the parameters. This type of problem is easy to solve if you just remember to follow the 6 steps. We're going to skip step number 3 and then return to it once we're finished step number 6. So let me show you how this thing works. Now, if you take a look at the statement here, z is equal to x minus mu over sigma, you'll notice that each of these here then, there's 4 different parts to it. And we need to know 3 of these in order to calculate the 4th. The z value always corresponds to some probability value on the table. The z isn't the probability, but when you look it up on the table, it'll give you an equivalent probability value, an area under the curve. So when the probability is given to you, we can convert it into a z value, and as long as we've got 2 of these other ones, we can solve for the last one. So let's take a look at a case where we're given a probability and the mu and the sigma, and we want to find the corresponding x. So consider again the marks for 50 students. The distribution is normal with a mean of 60 and a standard deviation of 12. What mark would you need? What x value would you need so that only 10%, that's a probability, which we can convert into a z, of the marks are higher than yours? So let's go through the 6 steps here. Step number 1. Step number 1 is, what do we know about the distribution? It's normal with a mean of 60 and a standard deviation of 12. It's the same marks for 50 students that we've been looking at. Step number 2, let's write this as a probability statement. We're looking for some value. Let's call it just little x. So that's a specific x value where 10% of the distribution is greater than that. Let's draw a picture of that. So here we've got 60, and we're going to find, this is the distribution of all x's, but we want to find a specific little x value so that this area here is 10%. All right? Right there. So what is that particular x value that gives us an area of 10% in the upper tail? Now, step number 3 is we need to skip that for now. And the reason for that is that, well, what we would have is z is equal to x minus 60 divided by 12. And the problem is we don't know what x is. That's what we're trying to find out. We don't know right now what z is, but we can figure that out from the 10%. So the point is that we can't do this right now. We have to jump straight to step number 4. And step number 4 says, let's find an equivalent z value to that 10% in the upper tail. Let's call that little z, so that you've got 10% in the upper tail. So that's going to be down here. I want to come up with some little z value so that we have 10% from this point up. Step number 5 is where you take a look at the cases. And the cases, if you look at the cases here, you will find that that is a case 2. So the important thing to note here again is I want you to get to a point where You're not using the cases sheet because you won't be able to bring it into an exam. I want you to just think this through. And what this is saying is that if this is 10% here, remember the table always gives you the area from some point down. It'll give you this area here. And so we know that that's going to be 40%. Whoops, 40%. Because the whole upper tail from 0 up is 50%. So what we've got here then is, case number 2 says the probability that z is greater than some little value z is equal to 0.5 minus the table value for z. So let's go back. Let me erase that first. I'm going to go back here. Oops. And here we go. And say that this is case number 2. And case number 2 says the probability that z is greater than some little z, which we know to be 10%, is equal to 0.5 minus the table value for z. And that means that the table value for z is equal to 0.40. And all that's saying is that's this area right here. Because the table always gives us the area from some z value down to 0, right? So if you got 10% in the upper tail, then you got 40% in that area. So what we're going to do now is we're going to go to step number 6 here, where we go to the table, and I think that's on about page 160 here. But we have to do this a little differently, because what we've got is, take a look at our picture up here. This is 40%, and so we're given the area. The thing to remember is that the areas are in the middle of the table here, and then you read out to get the corresponding z value. So what you'll notice is the numbers go from 0 all the way up to almost 50%. They get larger as you go across, and then you start the next line, and next line, next line, next line, until you get to the bottom. So what we do is we look down here to find the closest number to 49%. And here it is, right there. It's 39.97%. The next number right beside it is 0.4015. So the closest number then is 1.28. So we're reading, so this is really important, that the percentages, the areas, are in the middle. That's what those things are. And then we read out to the axes to get the corresponding z values. So this is 1.28. So let's go back to where we were. And so what we've got here then is that table value is equal to 0.40. So that gives us then a z equal to 1.28. Positive or negative? And that's where we take a look at our pictures. That's why it's really important to draw the picture here. And that's showing us then that we're on the upper tail, right? We're above 60, the upper 10%, so it's going to be a positive z value. So positive 1.28. Now what we do is we go back to step number 3. So step number 3 says that z is equal to x minus mu over sigma. And so we could solve for x here, where x then is equal to, and that would be equal to, let's see, if we multiply, if we take the mu over and then multiply by sigma and then bring the mu over, that's what we would end up with. So I'm just solving for x here. So that's going to be equal to 60 plus 1.28 times 12. And that gives us 75.36. So 75. So the answer is, and always go back and read the question to make sure that it makes sense what you get. What mark would you need so that only 10% of marks are higher than yours? And you'd have to get a 75 in order to be in the upper 10%. So that's how we do that. Now, I'm going to leave you the next two for homework here, but I want to set them up for you. So we're talking here about something called the interquartile range. And the interquartile range, we talked about that way back in Unit C. And so, I should have actually written down the page number here. So I'm just going to have to kind of guess here and see where we're at. Interquartile range, it's going to be way back here. So when we were talking, here it is. So this is back on page C20. And the interquartile range then is talking about the middle 50% of the data. So that's right here, the middle 50% of the values. Let's go back to where we were. So find the interquartile range. So what we're saying here then is, let me bring this picture over. And I'm going to set this up. Remember that we want to go through the steps. So X is normally distributed with a mean of 60, standard deviation of 12. We're still working on the marks for 50 students problem. And we want to find values that, let's call them X1 and X2. I guess if these were quartiles, you would call them Q1 and Q3, but you don't have to remember that. Q2 is your median. All right. But this is the middle 50%. So you got 50% here. Now that means that you've got 25% from X1 to the middle and X2 to the middle. So we want to find X1 and X2 so that 50%, that's what interquartile range means, is between those two. So I'm going to leave that there. I'd like you to go through, remember step number 3, you have to skip for now. And you're going to go into step 4. I'm going to leave you at step 4 and see if you can figure this thing out. All right, let's take a look at another one here. A bottling company wants to set its filling equipment so that on average only 5 bottles in 200 will contain less than a minimum net fill of 400 mils. What's all that about? Well, take a look at a bottling factory. And what you find here then is you can certainly imagine what the thing looks like, because you've got the thousands of these bottles on a conveyor belt, and they go along and they come to various places and so on like this, and various things are done. Obviously, an important thing is to fill the bottle up with whatever liquid that you have. Let's say it's some carbonated drink, and so it's going to be fizzy to a certain extent. What it does then is it comes in this thing, squirts in a certain amount of Coke or whatever pop or liquid it is that you're looking at here, and then it settles a little bit, and then it goes a little further, and then it fills up the rest, and it let that settle, and it might go a third time and let it fill a little bit more. I don't know exactly how it does it, but you want to make sure that it has a minimum net fill of 400 mils. Now, I probably could have put down 355, because if you take a look at a Coke can here, I think it says that there's 355 milliliters in it. And I don't tend to drink Coke, so I might be off on that number, but I think that's what it is. We're just going to make it a little easier and say, let's say it's 400 mils. So if you take a look at, say, a Coke can or any type of beverage can, even a beer bottle or something like that, you'll notice that it gives you the amount that is in there. So 355 mils, or in this case, 400 mils. The thing is that when you're talking about going along a conveyor belt and you're automating this system, you want to do this fairly quickly, there's going to be some variation in them. Now, what you don't do is you don't set the average to be 400 milliliters, or thinking back to the Coke can, 355 milliliters. You don't do that because that means that half of them are going to be higher than 355 mils, or in our case, 400 mils. I'll drop the 355. Let's just talk 400 mils. So higher than 400 mils, and then half are going to be lower. And most of them are going to be fairly close because of the processes that they're using. But every once in a while, you're going to get something which is, say, more than a couple of standard deviations away. And that could be noticeable. Now, if you look at it and it's kind of overfull, you get quite a bit. I mean, that in itself is a bit of a problem because it's under pressure. But it's a bigger problem when you've got it less than 400 millimeters, quite a bit less, where it's noticeable. So if it's in say a glass bottle, you could look at it and say, hey, there's not enough in here. And if you're a statistician, what you would probably do is you would pour the thing into some beaker and you would actually measure it, and then you would get angry and you would phone them up and you would say, I got shortchanged on this, and they would send you a case of Coke or something like that. And yeah, that's how they do that. So what they want to do then is they set the average so it's a little higher than the 400 mils. And what that means is that if the fills are normally distributed, which they will be, is you want to make sure that there isn't, it doesn't come out to be noticeable in terms of that you're really short. So if you take a look at what they do here, I'm going to use this picture here, bring this over. They're going to set some mu value. That's what we're looking for. And it's going to be higher than 400 millimeters. So that only 5 bottles in 200 are less than 400 mils. So this is the amount that they actually quote on the bottle. That's what's stamped on the bottle or on the can. Bottles, I guess we're talking. But they set it higher so that only 5 out of 200, which is 0.025, is less than 400 mils. So let's read through it. Bottle company wants to set its filling equipment so that on average, only 5 bottles in 200, so that's what we've got down here, will contain less than the minimum net fill of 400 mils, which is what is stamped on the bottle. Assume that fills are normally distributed. Are normally distributed with some unknown mu, but a standard deviation of 5.1 millimeters. That's right there. Okay, so we're looking at this. What's the probability that x is less than 400 is equal to 0.025? Now, the problem is that we have to skip that for now, because if you stick this into the formula, what we would have here then is, we don't know what the z value is. We've got 400 minus mu over 5.1. And so we can't do that. But this particular guy, the z, has a corresponding 0.025. So I want you to pick this up on step number 4 and follow this through, find out what case it is, go through, find out what that is, and you'll end up with the mean. I'll give you the answer. The mean turns out to be 410. So there's the answer. But I want you to get there. We will take that up in class. And that will take us into the last part after that.